Good afternoon, everybody, and thank you for being here today. Welcome to Space Center Houston on July 21st, 2019, not 2119 yet. 2019, 50 years ago today, the astronauts on the moon had finished up their initial lunar explorations and were getting ready to blast off back into orbit for a return eventually to the Earth. I am John Charles. I'm the scientist in residence here at Space Center Houston. I'm recently retired from NASA, and despite my appearance, I was not here during the Apollo era, but I got here as quickly as I could afterwards. I was only 14 years old, guys, when you were making history, so I was watching on those little black and white TVs as well. But I am deeply honored and very happy to be here today as the moderator of this very interesting panel. You have before you men of legend, people that developed the Apollo spacecraft system and made it possible to fulfill President Kennedy's pledge to land somebody on the moon and return him safely to the Earth by the end of the decade. We have on our panel at the far end Henry Pohl, who will be talking to you about spacecraft propulsion, but ended up as the director of engineering at Johnson Space Center across the street. We have next to me Mr. Tom Moser, who's going to talk to you about structures and materials, including some very interesting slides. I did get a chance to sneak a peek at his slides, and it'll answer some of the questions you have, and you can then go and talk to your friends that don't believe we went to the moon and answer some of their hoax questions. And in the middle is Mr. Jim McBarron, who has a great deal of insight into the spacesuits, those iconic white spacesuits that allowed astronauts to move around on the moon. He's going to answer some of your long-held questions about that. So with no further ado, I'd like to turn it over first to Mr. Henry Pohl to tell us about his experience with spacecraft propulsion throughout the space age, and especially in the Apollo era. Mr. Pohl.
Thank you. You know, 50 years ago is a long time, and I'm going to ramble a little bit about some of the things that I remember in trying to get there. You know, Dr. Gilruth said after Apollo that if we ever decide to go back to the moon, we're going to discover just how difficult it really was. And louder? Okay, is that better? Dr. Gilder said, if we ever try to go back to the moon, we're going to discover just how difficult it really was. And I think one of the problems that we had back then was it looked so easy when you watched it on your 19-inch black and white TV. You watch it Saturn V take off just as smooth. You watch the crew jumping around out there on the moon. It looks so easy to do that. But what most people don't realize is that Saturn V was drinking fuel at the rate of 20,000 gallons a second. It took the equivalent of 50 freight trains to drive the fuel pumps just to pump the fuel into that engine. Or engines, we had 5 of them. 90% of the weight of that vehicle had to be fuel. That left 10% for the crew, for the structure, for life support, for the electronics, computers, and everything else. 90% of the weight was fuel. That left 10% for Tom Moser and everybody else to worry about. The lunar module, they got one hanging up out here someplace. I believe 75% of the weight of the lunar module was fuel. We thought it was going to take 85%, but as time went on, we were able to get that down just a little bit, get a little more forward for the other stuff. What are you? You know, it's kind of difficult for us to remember what life was back in the 50, 60 years ago. I say 60 because it's really 60 years ago when we decided to go to the moon. And so we had to live with what was available then that could be very quickly developed at that time. You know, we had no computers, we had no cell phones, we had vacuum tube TVs. And you just think about that a little bit. It's almost like when Kennedy told us to go to the moon in 10 years, that was almost akin to telling us to build an automobile that'll go 500,000 miles. Now that 500,000 miles had to be with no filling stations, no repair shops, no food. You had to carry your food with you. You even had to carry the air with you that you took up there. And we had to do all that with 10% of the weight of the vehicle. And none of that, and I don't know how to get it across where that's easy to understand. It's not easy to understand how little of the weight of that vehicle was something other than fuel. That Apollo 1 fire, as bad and as horrible as it was, probably was the one thing that did more for the success of the Apollo program than anything else that we did. That woke a lot of people up. It gave us an extra year to develop the maturity and the hardware to make some very needed changes to the program. And I think that more than any other single thing made it successful. But you know, it's just not normal for earthbound humans to think in terms of the absence of gravity, the absence of pressure. We take those things for granted. But if you remove gravity from a pot of water, you can have a pot of water and put it on a stove and it'll get hot, boil up water. You put a pot of water on a stove and remove gravity from it, and the water gets hot on the bottom, forms a big bubble. The bubble pushes the water out of the pot, or burn the bottom of the pot, or the pressure will build up in there and blow it up, and the water will stay cold. You watch the crew running around on the moon up there. It looks so easy, it's so simple. You don't realize that the side face of the sun's almost 250 degrees. The side facing deep space is a minus 250 degrees. That's almost a 500 degree difference. At least not quite 250, but close to it. You got to contend with. Not only do you have to take your air and food with you, but you also have to contend with huge temperature changes. I think that was our biggest problem in designing, certifying the propulsion systems, was trying to get them to work in a vacuum, trying to get them to work without gravity. We had no experience in this country at that time operating without a gravity, without a pressure. You know, you put gas in your tank of your automobile, and it'll suck every drop out of the tank before you have to put more gas in it. You put gas in it in 0G and start using it down, it just sucks the bubble right down through that gasoline. And rocket engines didn't like bubbles very well. So you had to contend with that. We were able to build very good vacuum chambers. Matter of fact, we could build vacuum chambers that came very close to simulating the sun, came very close to simulating deep space, but we never were able to develop anti-gravity machines. We did use a vomit comet a little bit, but that was late. You wouldn't think that a vacuum would have that much to do with a rocket engine. But all of the manifolds are empty. We used acid-base propellant, so the service module and lunar module, that was self-igniting propellant. And when you try to start them in a vacuum, the evaporative cooling would overcome the heat generated from the acid-base reaction. And a lot of propellant would accumulate in there before you'd get enough to ignite and you get a hard start. We did have a lot of problems with stability on the early engines. As a matter of fact, I remember I got a call one night about midnight from the FBI. They had one of our guys in jail in Sacramento. And what happened, he got on an airplane and he and his buddy was talking about bombing the engine. Well, the stewardess heard him, went and told the pilot, and they hauled him off the plane. He spent the night in jail because he was talking about bombing the engine. What he was really talking about was putting little bombs in the little detonators in the rocket engine. We'd start the rocket engine and then turn that on and then put a pulse in the chamber, try to damp it out. You know, there was very few times when we weren't thinking about work or talking about work, day or night, on the job, off the job, no matter where we're at. One of the problems that still haunt me is how close we came to missing the one on the propellant tanks. About 28 days into a 30-day test, we had a very tiny leak in the oxidizer tank. They cut that piece out, sent it off to a testing laboratory to have it tested, and they came back and said it was a fingerprint. I looked at the failure report, sounded good to me. I signed it and sent it off. And I don't know, maybe a month later, I had two guys come in my office. Henry, we can't let them get away with that. That was not a fingerprint. It'd take a monkey to get their finger in the hole of that tank. We had about a 2-inch hole in the bottom of the tank where we put the standpipe stuff in it. Every morning they were in there. Henry, we can't let them get away with that. We got to do something. I said, well, tell me what to do. I don't know what to do. They finally said, put 10 tanks in test, and if 10 tanks go through it, we'll say it's a random failure and let it go. So we did. 96 hours into the test, one of the tanks busted wide open. Before they get the pressure off the other 9, 2 more busted wide open. Finally traced that down to the fact that the manufacturer of the propellant had changed the manufacturing process, and it had free hydrogen in it, and titanium don't like hydrogen too much. So we had to change that. Had we not caught that, it would have caught us on one of the flights. There's so many things like that that we worried about all the way through the design, certification, development program was what we forgot, what might go wrong, what could go wrong. And we were just very, very fortunate to have thought of most everything, caught most everything. so that the flights went off pretty smooth. I remember on the lunar module when we landed, we had a heat exchanger freeze up on the descent tank, and we had to mess with that for a while. We were afraid the propellant lines was going to bust, but they didn't. They thawed out and relieved the pressure on it. Descent was an interesting development program. You know, the first time we had a deep throttling rocket engine. Throttling of that rocket engine was about, we were supposed to have 11 to 1. I think we only got about 9.8 to 1 was the best we ever did on the thing. But it had a tendency to chug when it would go unstable. You couldn't put baffles in it because of the way it was designed. But that was a challenge. Chamber pressure is down as low as 10 psi and up to 100. The Ascent engine, we had problems with stability on it. We finally gave up on it and let a backup contract for another engine very late. And we developed and qualified that engine in probably less than a year. I don't remember the exact dates on it now, but something like that.
A bit of a short course on the very complex issue of spacecraft propulsion. You don't get that just anywhere. Next, I'd like to have Mr. Moser talk a little bit about the structures and materials of aspects of Apollo.
Thank you very much. Before I start that, let me put things in perspective, if I may. You're looking at the screen with the Saturn V launch vehicle. As Henry said, it's about 90% fuel. At the very top of that is a little cone. That's where the 3 astronauts resided. And when it came back to Earth, it weighed 12,000 pounds. When it lifted off, that entire stack weighed 6.5 million pounds. So you can see what we brought back and what it took to get there. I'm going to talk to you a little bit about the rocket at the top of that cone. I'll do that in a minute. And then about the flag and a little inside story on that. But first of all, I see a gentleman down there with an LSU T-shirt on, I believe. When John Kennedy said, put a man on the moon, return him safely to Earth within the decade, we didn't know what we didn't know, okay? We'd never put a person in space before. John Glenn had never been in space. We didn't know if humans could function in space. We didn't know if we could rendezvous in space, which we need to. We didn't know how to navigate to the moon. There's a lot of things we didn't know. But one thing we had is strong leadership. And a person from LSU, Dr. Max Vijay, who was all of our bosses, led us through that. There was another person that is very critical to this. How many people know the name Chris Kraft? My wife and I just left Chris Kraft at his home. He's in hospice care. He may live through the rest of this meeting or he may not. So Chris Kraft is a person that led us all from the very beginning all the way through. It takes strong leadership by the president. It takes strong leadership by people like Max Vijay and Chris Kraft to get us there. There's a full commitment on everybody's part. So I just wanted to recognize that it's engineering that does it. It's astronauts that work together, and it's flight directors. All 3 of those entities have to work together all the time to make it a success. So this is the launch vehicle, and I've already said what I wanted to about that. We're going to talk about that little thing at the very top. I'm going to give you a little bit of engineering insight into what structures and materials engineers do. Okay. We found out early in the program, it's like about 1963, one of my first jobs was if the rocket has a problem and the little rocket at the top of that stack has to pull the astronauts away, we found that at very high altitudes, everything was fine. The astronauts could maneuver the spacecraft to come back in. At lower altitudes, in the center section you can see there, we had a problem at anything below 120,000 feet, and that is the spacecraft would come back with the pointed end first, and that's where the parachutes were, and it couldn't deploy the parachutes. So Max Vijay talked to the contractors. They said, oh, we can do that. It's going to cost you, millions of dollars to do it. We said, well, Max Vijay said, look, I can do it in my garage cheaper than that. And the garage was at the old Canada Dry Works on the Gulf Freeway. Probably most people in this audience don't know about that, but it's where our technical services were. Another engineering myself, Clarence Wasilski, figured out a way to split the skin at the top of that little rocket so that when it lifted the command module away, it would turn the command module around so that the pointy end was away from the velocity and we could get the parachutes out. So that was our, what we called canards. So one of my first jobs there, that's when I had a lot of hair in the lower right-hand side and was not bald, and I'll tell you why I lost all that. But we went, my first job at the Johnson Space Center in 1963 was to take that thing to Langley Research Center, deploy it in a wind tunnel, and see if it worked. Lo and behold, it worked. Next thing we did, we put it on the top of a Little Joe rocket, took it out to White Sands, and demonstrated it would work. So lo and behold, we were ready to go. Now we could tell the contractor, this is how you do it. And so that's the way we did all of our human spaceflight programs. We did a lot of engineering ourselves. We didn't manufacture the flight hardware. Another little story, a little inside story. This was happened, the first one was in 1963, a long time before the 1965 flight of Apollo 11. However, 2 weeks before the Apollo 11 flight, my boss, who was a guy named Joe Katanchik, came in to my office late one evening, probably 7 or 8 o'clock at night, said, you're going to work on something. And he said, you can't talk to anybody about it, and we're going to put a flag on the moon. The problem is, the reason you can't talk to anybody about it, is there's an international agreement that we will not claim the moon so that we can't put a flag on it. However, Congress wants a flag on the moon. So he said, now then, here's your challenge, okay? You can talk to a couple of people in the technical services division. They could make things. You know, us engineers with slide rules, we couldn't make anything. So you work with a couple of guys over there, and you figure out where to put a flag, put it on a staff and something to deploy it. It cannot go in the lunar module. There's not room. So you have to figure out where to put it so the astronauts can retrieve it easily when they get on the moon. And beside that, tell them how far away from the spacecraft to put it so it doesn't blow over or burn up, and then tell them how deep to put the staff in the ground. I said, yes, sir. So we built something. There again is me with a lot of hair and the dark hair, and but that was an engineering mock-up of what we had for Neil Armstrong to plant on the moon, Neil Armstrong and Buzz Aldrin. So that's what the assembly looked like. We folded that sucker up, and as you can see below there, we wrapped it in some thermal insulation so it wouldn't burn up, put it inside of a metal container at the very top, and then we said, okay, we can take that and we can put it on the rail of the ladder. So that's what we did. Now then, that would be easy for Neil Armstrong to reach up, take it down, pull it out of all that stuff we had wrapped around it, and deploy it. So we did a little vibration test on that to make sure it didn't shake it. Don't forget that ladder was probably designed for about 50 pounds of weight on it. So now we hung something else on there. And so the question was, and don't forget, I couldn't talk to any other engineers about this, is to make sure it didn't break the ladder. So I took out my slide rule and I did some analysis, and lo and behold, I thought the ladder was strong enough. Put it on a shake table vibration. We shook the hell out of it, and it didn't come off. And we've got something that's called an equivalent load factor. That means so many G's to calculate what that little mass was we hung in there, make sure it didn't break. And so I said, we're good to go. Took it to the Cape, showed Neil Armstrong how to do it, and Buzz Aldrin. And so the next thing we know, we packed the flag. That's when we took it, and there we are packing the flag to go to the moon, to go hand off to Armstrong and Aldrin. And then the next thing that happened was, I hope the slide comes up. I did. There it is. So here comes Buzz Aldrin down. You can see on the very left-hand rail, the flag package there. They came down, and there was something that happened just before that. When Neil Armstrong got down to that last rung, he jumped. I was watching on black and white TV, but I knew what happened. I knew that damn ladder broke. And if it broke, you know, there was probably a sharp edge. If there was a sharp edge, it probably cut his spacesuit. If it cut his spacesuit, he'd die instantly. That's when I lost all my hair and it turned gray on that flight. So that was a little surprise. The other surprise on this was when they deployed the flag, the horizontal rod up there was a telescoping rod, and it wouldn't extend all the way. So the rod was shorter than the flag was long, so therefore it looks like the flag is waving. Many people think this is all a conspiracy, it's a fake, you know, since there's no atmosphere on the moon, it can't be waving. Well, that's the reason it was waving. We screwed up, okay? But, you know, not wanting to admit too many errors, we made, after that on all the other 5 missions, we made that rod just a little bit shorter than it did, so all the rest of them look the same way. So anytime you hear the flag is waving, it's because it's all fake, not true, the earth is really round. So I told that story to Buzz Aldrin in the Aerospace Museum. Buzz didn't know all that. He knew a lot of things I didn't know also. But anyway, it was the thing that's true about all this Apollo thing. It was our nation's commitment to do that, okay? We did it, okay? And it was the full commitment by the President, by the Congress, by the people to do it. Technically, it was a huge, huge challenge to accomplish all the things that we did, but it's a thing that we should all be proud of, and we will. It was easy politically. It was extremely hard technically. Space station is extremely easy technically, very difficult politically. So we're in this conservation of complexity that we do. Okay. So that's it. I was going to talk a little bit more about canards, but I'm going to pass on that. And I'll pass that over back to the moderator here.
Thank you. Thank you very much, Mr. Moser. And I think, if nothing else, here today, you can now go and answer anybody who doesn't think we landed on the moon, that thinks it's all a hoax. You can say, we have the ultimate proof, Tom Moser is bald. And our final speaker today is Jim McBarron, who has lived through and actually lived inside of the history of spacesuits. So, Mr. McBarron, please.
Good morning. Before I start with my slides, I would like to acknowledge the 3 crewmen who lost their lives on Apollo 1. Gus Grissom was a friend of mine. He flew on the 2nd flight of Mercury, a suborbital flight, MR4. He also was the first crew member to fly on a Gemini flight. I miss Gus. Also, Ed White, who flew on the 2nd flight of the Gemini program, made our first spacewalk. And while it was only about 15 to 20 minutes long, it did prove to us in the spacesuit world that the thermal insulation protection garment that we had designed would work in space, in the vacuum of space, which led us to proceed with the additional Gemini EVA spacewalks and eventually in the Apollo program. Now, my subject, which is a challenge, is the impact to the spacesuit program resulting from the fire and the loss of these 3 courageous crew members. Immediately after the fire, the Apollo program management made a dictate that we should immediately cease all oxygen-enriched atmosphere operations and testing until we could know what we were doing right and what we were doing especially wrong. Because you see, the inside of the spacecraft was pressurized with 100% oxygen. Likewise, during normal operation, EVA, the spacesuit is also pressurized with 100% oxygen. In addition, the agency was no longer going to do any manned testing in an oxygen-enriched environment, especially by the contractors who were designing the life support system on the spacesuit. In addition, before we commenced doing any additional manned testing in an enriched oxygen environment, and that they would always be done in NASA facilities and only after the completion of an operations readiness inspection, or ORI. Now, what an operational readiness inspection was a review by an independent group of facility and safety managers and engineers to assure that the facility side of the test did not present any hazard or risk to the person conducting the test, especially when we put a crewman in a suit on the ground level at 14.7, 100% oxygen, which we did when we ran into vacuum chambers to qualify the system. In addition, we would identify and eliminate all potential ignition sources in the oxygen-enriched environment, and to remove all flammable materials from this oxygen-enriched environment that was possible. Now, it was recognized that that couldn't be done 100%. And that's when there was a requirement that the supplier of the material that was going to go inside the spacecraft had to provide what was called a materials usage agreement, which was reviewed again by an independent group of materials experts, safety personnel, who made a recommendation to the Apollo program manager that it was acceptable to use this flammable material and that all reasonable means had been taken to eliminate it or to provide protection so that it would not be suspect to an ignition source. Now, the challenge to the spacesuit people was that the suit is a flammable system, and it had 100% oxygen on the interior. At the time of the fire, the design of the suit had been essentially completed. We were in a process of building training suits for the astronauts who were going to fly on their first flight. Production of the certification suits that we would use to certify the system was in production, and some of the suits were actually being tested. In fact, at the time of the fire, we had a crew member getting ready to go in a thermal vac chamber here in Houston to qualify the suit and a backpack operating together in what was called an extravehicular mobility unit, or as we called an EMU. The design of the suit at that time consisted of a separate jacket and pants outer layer, which would be put on by the crewman just prior to taking the spacewalk on a lunar surface. At the time, as a result of the fire, this approach was not valid anymore because it would expose the interior of the flammable suit to any potential ignition opportunity. So it was required that we delete the separate jacket and pants configuration and provide a completely covered suit with a non-flammable layup of materials over the torso, arms, and legs. In addition, the boot soles, which were a neoprene, had to be changed to a Florel material, which was non-flammable. For all the flammable materials that remained, we issued the materials usage agreement, which is eventually approved by the program. Of course, the crewman had a helmet, And to be able to see, we had a material called polycarbonate that was covered the visual field. And that was a large surface area that we could not change to a non-flammable material because the technology just didn't exist for that at the time. The back of the helmet has a vent pad which distributes the flow coming from the life support system to provide fresh breathing oxygen to the crew member to his oral nasal area. That vent pad was made out of a polyurethane material which was extremely flammable, and when exposed to exceedingly ignition source would violently explode. At the time, we covered that material, that vent pad material, with a non-flammable material, and received approval again by MUA for its use. Likewise, the extravehicular visor assembly, which was required on the lunar surface to provide solar protection to the helmet, as well as cold environment protection if the crew member was inside of a dark crater. We had a temperature requirement that the system was to provide protection from minus 250 degrees Fahrenheit to plus 250 degrees Fahrenheit. Quite a temperature range. So we ended up covering the polycarbonate shell that was on the back of the EVA, as we called it, extravehicular visor assembly, with again a layer of non-flammable materials. Likewise, we covered the gloves with non-flammable materials. That gray material you see on the gloves that provided protection from an ignition source was a material called chromalar. It was a woven fiber of nickel and chromium, 90% nickel, 10% chromium, that was woven into a fabric that provided the required non-flammable characteristic as well as abrasion and strength protection to the gloves bladder on the inside. There was a suit harness on the inside that provided for communications as well as bioinstrumentations for the doctors to monitor the medical condition of the crew members. We covered that harness with a non-flammable material called Teflon. It was a woven Teflon material which provided the protection that was necessary. And that material, which was exposed somewhat, again had a MUA on it. Inside the suit, the helmet, the crew member wore what we refer to as a Snoopy hat. You've probably heard this term. And it provided the redundant microphones and earphones so the crew member in the suit could communicate with the ground and the other crew members. The dark colored material you see on the sides of the comm carrier, again, is woven Teflon fabric, providing the non-flammable material. Now, inside the suit, which was protected by the outer non-flammable cover layer, were materials that could not be changed. These included the constant wear garment that the crew member wore when he was in transit from the Earth to the Moon and back to the Earth, and to the liquid cooling garment, which was required to provide cooling to the crew member when he was extravehicular or doing a spacewalk on a lunar surface. And the waste management system provisions in the suit were all left alone and were approved again by a materials usage agreement. This is my last slide, and it shows the different materials that were used to provide the protection that I just discussed. The outer materials of the suit was developed by Owens Corning and DuPont for us, and it was called Beta Cloth. Beta Cloth was a woven silicone glass material that would not burn. And that was what was used as a basic non-flammable material that covered the complete outside of the suit and those areas of the suit where we didn't have the chromalar fabric or the Teflon. Now, we had Teflon patches to provide abrasion protection that were on the outside of that layer that was necessary. And if you looked at that total layup that's shown there, there's 21 layers of different fabric that is provided to provide the non-flammable characteristics of the suit, as well as meet the characteristics for thermal and micrometeorite protection, as well as a pressure envelope to keep the pressure at a safe level within the suit so the crew member could perform his assigned job on a lunar surface. Thank you.
Thank you, Mr. McBarron. What I'd like to do now is open it up for questions from the audience. We have about 15 or so minutes for Q&A, so if anybody has any pressing questions about the spacesuit, and again, you've received a short course in spacesuit development. Now you know why the suit's white and why the helmet has visors on it and all that kind of stuff. So let's take questions from the audience. Yes, sir.
How many layers of this spacesuit were actually containing the environment? How many layers did you have that were able to contain the oxygen-rich environment?
Let me repeat all the questions so we get them on the recording. The question was, how many layers of the suit were required for containing the environment? What was the airtight structure of the suit?
The airtight structure of the suit, or the interior of the suit, was mainly a neoprene-coated nylon restraint, and the mobility joints were a form bellows, which was a proprietary compound developed by ILC Dover, which was a subsidiary of Playtex, and it was a fallout of making girdles for women back in those days. Actually, the outer layers, the non-flammable layers of the suit, the most outer layer was a layer of that beta cloth that I referred to. And then as part of the thermal insulation, we had several layers of Kapton, which is a non-flammable plastic film. And it's gold colored on the outside, as you probably see on the outside of the lunar module as well. And then the rest of the thermal layers were interspaced layers of aluminized perforated mylar separated by what we called a scrim of Dacron. In order for essentially the thermal layup of the suit was based on cryogenic type thermal insulation, where you have multiple layers separated from each other that allowed the vacuum to escape, and that's why it was perforated, and provided the thermal protection that was required to keep the suit in a normal operating range. We had abrasion patches on the outside of the suit of the woven Teflon, which is non-flammable, in the high abrasion areas, or the chromolar fabric I mentioned previously. I hope that answers your question.
Let me just note that this is once again proof that the program was not faked. No fake program would claim the suit was made by a ladies' undergarment manufacturer. Are there other questions? Yes, sir.
So I know that if you're familiar with the new suit design that's coming out, so I wanted to hear your thoughts on that and then yoga pants in general.
I don't know if you know, but I just spent a whole week at a preliminary design review as a, quote, expert consultant on the next suit system called the Exploration EMU, which will first be a demonstration system for use on the space station, and then any mods required for that to go for the lunar landing on 2024 that the president has dictated. My impression of that suit is that at this point in the development, they are well along with understanding the requirements and what they're doing and in the approach for the design. See, when we did this, we didn't have knowledge as to how to do it. I mean, we were the first ones, which made it a lot harder because we learned by trial and error and many failures. This group that is doing this, quote, Exploration EMU, or XEMU as they call it, are extremely talented engineers from my perspective. They're well along on the design, much further along in the design than what we were at this point in time at a PDR. A PDR is a preliminary design review. Usually you just have your requirements well documented and discussed, and concepts of how you're going to do the design. Well, in this program this past week, I learned that they have actually had to design and test in a lot of the subsystems. They've picked the systems that they're going to use to build the components. They've identified the contractors. And what's different about this system, it's not going to be designed and built by a contractor. It's going to be done in-house in crew systems and at the JSC with the supporting elements and materials and all the test facilities are available. So it's going to be an interesting project, and I'm looking forward to continue working on it, actually, as a consultant, of course.
Good, good. Over here, yes, sir.
How can you protect astronauts from radiation, specifically from Van Allen belts?
How are the astronauts protected from the Van Allen belt radiation?
Well, during Project Mercury, this first subject first came up, and we actually developed a lead apron that we would have worn on a suit, and a very thick, 1-inch thick plexiglass visor that we would have put on the helmet if it was necessary. But in evaluating the requirement for protection for the Van Allen radiation belt, which is around the equatorial plane of the Earth's orbit, it was found by the experts in that field that we didn't have a problem with the layup that we were using in the suit, and we should proceed on without any added extra protection. Now, when we go back to the moon, that's going to be raised as an issue again, because we're probably going to land on a different part of the moon, which might be subject to a different part of the radiation from the sun. So it's something that's going to have to be looked at for the future.
Yes, in the back. Right there in the middle. Yes, sir, you. Yes.
I was curious, for the simulation for micrometeorites and such, did you have a way of testing that before you went on the mission?
Question is, how did you verify protection against micrometeoroids?
Could you repeat the question? I didn't
How
hear.
did you protect it? How did you verify the suit was going to be protective against micrometeorites?
Okay, and for Apollo, out at Ellington Air Force Base, we had a gas gun which would fire a very small projectile at a very high velocity, which we shot at cross-section samples of the thermal micrometeorite garment to verify that these small particles would not penetrate the bladder and cause a leak. Now, we weren't able to, with firing even with a very high projectile gas gun, as we called it, you couldn't get the speed of a particle fast enough to hit the target. So we used an equivalent energy mass formula that the scientists and engineers and the materials were developed to equate the energy that was expended in hitting the TMG cross-section so that it would provide the protection required. And we found that the multiple layers of the super installation and added 2 layers of neoprene-coated nylon on the backside as a barrier provided the adequate micrometeorite protection that we required for Apollo. Hope that answers your question.
Okay, other questions? Yes, sir, against the railing. Yeah.
I have a question as far as the Apollo 1 fire, you had the flammability of the pure oxygen environment. Russians kind of always did like a mixture of nitrogen and oxygen like on Earth. But the problem is when you do EVA, that you start running into problems like the bends. The Russians, I believe, they jacked up the pressure on the suit. I was wondering how seriously was that considered?
Question is, how seriously was a different atmosphere considered that would have been more protective against fires, but perhaps more promoting of the bends?
The bends is an issue. Before going EVA, the crew member must pre-breathe oxygen at the correct atmospheric pressure to expel the nitrogen that remains in the tissues of his body, which would end up creating what was called for undersea divers, the bends. The Russians used a different protocol for the bends than we do, and we have been in the shuttle and the station world have developed a new protocol that before going to the low operating pressure of the suit, we first lower the pressure within the airlock, and the crew member breathes 100% oxygen on a mask before the atmospheric pressure of the airlock is reduced down to the operating vacuum condition. Hope that answers your question.
Yeah, I think the rest of the story is it was never really considered on the American side. I think the suits are always going to be 100% oxygen. Let's see in the, yes, front row.
Can you do a little comments on the backpack? On the back of the suit, what was involved with cooling and whatnot?
Yeah, can you talk a little bit about the PLIS, the backpack, the cooling and so forth of the PLIS?
Okay, my expertise is in the field of the spacesuit, which is the actual clothing that the crew member wears, but I can answer your question about the PLIS. The Portable Life Support System is an air-conditioned system that keeps a crew member cool as a cooling system. It provides a supply of oxygen for replenishment in the atmosphere that he breathes, and when he expels the CO2 as breathing, it has an absorber that absorbs carbon dioxide, absorbs or finds a way to, technology is advanced that they have a way now to remove the CO2 from a cartridge by expelling it to a vacuum source and then replenishing it by putting it back into the system. So it has a system of thermal control, provide fresh breathing oxygen, and removing carbon dioxide, all in a small little package you wear in your back. That's a closed loop system. And the new system they're designing is being designed for an 8-hour spacewalk, and Apollo was designed for a 7-hour spacewalk.
In the back, yes, ma'am. The question is the role of programming and computer programming and the design and the operation of the Apollo era hardware.
Let me comment to kind of put it in perspective. On the command module computer in the memory, it was less than 1/10 of a megabyte. And how many people out here have an iPhone, super iPhone? That is, compared to 1/10, your iPhone has 64,000 megabytes. So that puts it in perspective. There was a lot of stuff done on ground, and communicated up. There's not a lot of onboard computing like there is today in the space shuttle, and certainly not in some of the things for the future. So it'll be a lot more onboard computing than there was at that time.
Yes, ma'am. The question is the Saturn V powerful enough to escape the galaxy?
I think the simple answer is no.
No. Not yet, but it's being worked on.
No, not the Saturn V.
Not the Saturn V, no.
The question was Saturn V.
Leroy Chow is working on a hypervelocity type rocket propulsion system.
All right. Yes, sir, in the middle.
What was the actual mechanism that provided the cooling in the PLS?
What was the actual mechanism for cooling of the PLIS and the LCVG?
We used a water supply that was carried in a tank through a valve and regulation system to what was called a sublimator. And through the process of sublimation of water into vacuum, it required absorption of heat. and the heat came from the heat exchanger sublimator, and the heat got away from the crew member through the liquid cooling garment that was cooled going through the sublimator process.
Yes, waving your arm.
When you mentioned about the lunar lander ladder breaking, was there ever any investigation done about it, and why would Neil not mention that? How would have been aware that it broke?
I don't think the ladder actually broke. I think that was his concern.
No, the ladder did not break. Let's make that very clear, okay? So my analysis was correct, and I was happy, and so was he.
I think maybe part of his confusion was that the landing leg didn't collapse as much as had been expected, so there was still a high step from the end of the ladder down to the landing pad.
Actually, there was a distance between the lower rung and getting onto the lunar surface, and he jumped, okay? That was part of his plan anyway. Well, I didn't know his plan. When he jumped, I thought the ladder broke. We tried to tell him everything. He didn't tell us everything.
Yes, ma'am. Yes.
I'm wondering, since like the movement of the human in moon it would be different from the movement in the Earth, is there any biomechanics aspect that is considered when you design a spacesuit?
Yeah, the question concerns the differences in the biomechanics of ambulation and movement on the moon at 1/6 of a g in a vacuum versus on the Earth. Did you take into consideration any different aspects of mobility on the moon?
We looked at that somewhat and couldn't make a determination if there was going to be a difference. But we did feel that by training a crew member and designing the system to operate at 1 gravity here on Earth, that it would give us a margin for operating at 1/6 gravity that's existent on the moon. So in the post-flight discussions with the crew that I was involved in on the EVA debriefs, the crew member told us that there were differences for 1/6 G, that it was easier to move, and you had to be careful to not lose your balance. In fact, a couple times I think you've seen crew members fall down, but they were able to get up easier than they can on the Earth, they said, as far as springing up using the muscles in your legs. So we didn't have any specific requirements to design to for biomechanics between the Earth and the moon, except to acknowledge that there is a difference and to do a lot of testing. We had 1/6 G simulator where we trained a crew compared to the operation at 1 gravity. So it's worked out fine so far.
Anybody in the back? Let's see. Yes. Go ahead.
So I don't know if I heard this correctly, but I think it was mentioned that small explosives were being used to ignite the engines. Could you describe maybe how that was done in a safe way?
Yeah, Mr. Pohl, the question concerns, were explosives used to ignite the engines initially?
I don't understand the question. Could you
On the
repeat?
command service module, we used the acid-base reaction to form the ignition process. We used a very strong acid and a very strong base. Nitrogen tetroxide was oxygen, and monomethyl hydrazine was used for fuel. Now, the problem you got into when you used a vacuum or try to inject that into a vacuum was it would freeze, and the freezing process would lower the temperature faster than the heating process from the acid-base reaction. But no, we did not have any explosives on any of the service module descent, ascent, or RCS engines.
The question was, how did you overcome that issue?
On the RCS, we built a little chamber in there to contain the gases together long enough for them to heat up and ignite. On the big engines, we changed the ignition process to where we brought one fuel in and let it to boil off to where you built up a little chamber pressure from the gases and then brought the propellant in.
And I think the initial question about the explosive, that was a technique that the engineers used to induce instability in an engine to see if the engine could recover its stability. I don't think there's any intention of igniting an engine with an explosive. Ladies and gentlemen, that concludes this presentation. We've run out of time. We have many more questions, I'm sure. Thank you very much for being here today.